for people here, but I can only do so much. So we're going to start with interaction terms. Currently kind of got that problem set and that quiz. In fact, I forgot to change this. I told you guys I was going to change this so that they're just both set to be due at the end of next week. Okay, so go in right now so I don't forget by the time I get back to my office. Let's have these set to be due both at the end of the day, Friday next week. You got those practice problems for the quiz. You have the due file about related to nonlinear relationships to kind of help you with that problem set 4. And then today we're going to move on to talking about interaction terms. Okay. Any questions for me before we jump into material here? Yeah.
So is quadratics, like comparing that to a log linear or a linear log, is that just R squared or is it different? Do you have to use
So we can only compare those models. Which models can I compare my quadratic to? What has to be the same? So if I'm using my R squared, I have to have the same dependent variable.
So you can compare your quadratic with the linear log.
Correct.
And that you can just do R squared with.
Correct.
Okay.
In addition to that, I'd have to do something like we're talking about. We didn't really talk actually about how we can compare to the other types of models. There are tests that we're not going to cover, but they're much more difficult because we don't have the same variation in our Y variable. So it's very, very difficult to compare those models without additional topics outside the scope of this class. Does that answer your question? Okay. Any other questions before we jump into the new material here? So what we're going to be doing today is we'll start back with our kind of linear model, right? And we'll kind of build upon that again. So we're kind of getting away from nonlinear. We're just going to look at linear relationships again. However, we're going to allow it to vary for groups, right? So I had this kind of example where I'm thinking about wages. We've got a data set, which we'll kind of dive into. And I've got other controls, but for right now, let's just think about 2 simple controls. One is just a dummy variable for whether or not the individual was identified as female or not. And then a 1 for whether or not they were married. So we'll start out with 2 dummy variables. We'll eventually move to continuous variables, but for now, let's just think about if we had these 2 dummy variables. So how would I interpret beta 1? It'd be my predicted change in the wage if the individual is female. What would beta 2 be? Predicted wage if the individual was married, right? So nothing crazy new here, right? We can run this regression. Now I'm using the log of wage. So just to get a little more practice, we typically think that when we're using wages, you'll see like if you were to Google research that's done on it, they usually use the natural log because the same, I think I mentioned last class, like going from $10,000 to $20,000 of income is much different than going from 110 to 120. So percent changes matter a lot more with wages. So here it gets a little bit tricky, but how would I interpret my female coefficient from that regression if I use the natural log of wage? So it's the effect of being female on my wages, right? But it's the predicted decrease here. Would it be, it goes down by $0.38? If I'm going from like a level to a log, I would need to take that coefficient. Remember, natural log is like it's not completely correct, but it's like we've converted it to percentages. So what do I need to do? I'm going from proportion to a percentage. I need to multiply by 100. Right? Okay, so that's not technically quite correct, but it's the right. I think it's an easier way to think about it. So here, being female would actually predict that wages, and I believe these were hourly wages, would go up by what? 38%, right? If we're moving the decimal to, or sorry, not up, down by 38% here. Now, we probably have a lot of important omitted variables. We're only got an R squared of what, 38%. We want to put in percentages here. But that's how we could start to interpret these coefficients. So looks like being married increases your wage, being female decreases it, and they're pretty statistically significant. So why might we want to kind of continue to look further? Well, maybe in the workplace, it's like right now we see females being kind of treated negatively, right? Now this is some older data. That's the good news. The bad news is the sign of the effect still looks the same with newer data, right? But maybe that group is being treated differently dependent on if they're married or not. So maybe it's not just being female is decreasing your wages. Maybe a married female in the workplace is treated very differently or viewed very differently as a married male, right? So maybe the married male, employers don't view them as like having a lot of additional, responsibilities, even if they have children. Well, maybe the married female, they think, well, she might have a child, she might, be out of work. And so maybe there's a difference in the effect of being married for a male versus a female. Okay. So what we can do is include this interaction term between the two, right? And we can then start to think, well, what's the total effect of being married? Well, this is where it's going to vary, right? So if I think about my regression, and here we have the natural log of wage, and I've got, and let me make sure I'm doing this in the same order as the slide. So this was female, this was married, and then we included an interaction between the two, which was simply taking that married dummy and multiplying it by my female dummy. Now, it's kind of weird, but I've really created three categories here, right? So what would beta 1 be the effect of? So it would be the predicted change in wage from being female. However, what kind of female? If the individual was married, well, then the effect of being female and married would be beta 1, but also 1 times 1, you would also have beta 3. So for beta 1, that's going to be the kind of predicted natural log of wage or predicted wage for a female who is unmarried, right? Or the 0 group of the variable that we interacted it with. Now, what would beta 2 be? This is going to be the effect of being married. But for who? If it's a female, it wouldn't just be beta 2, it would be beta 2 plus beta 3, right? 1 times 1 here. So beta 2 is going to be the effect of being married for males. I guess maybe if I'm trying to keep these right, males right on the same side here. So what about beta 1 plus beta 3? This is going to be the effect of what? A married female? Well, what did I forget? If it's a married female, I not only have beta 1, I not only have now beta 3, but I also have beta 2, right? I would have all 3 of these coefficients. Right? So this is going to be the effect of, for a female who is married. Okay. So if I'm looking at this, anytime I have 2 dummy variables, right, they can be 0 or 1, 2 times 2, there's going to be 4 different groups. Well, I've got 3 here, married males, unmarried females, and married females. So what's the group that was left out of this regression? Not married males, unmarried, right? So whatever the 2 0 groups would be for these 2 dummy variables. What's the effect of that? Well, it's just, that's kind of my baseline, right? This would be 0, 0, 0, 0. The only predicted wage, the only coefficient that matters for these unmarried males would just be beta 0. Now, in fact, if we were making predictions for every group, beta 0, the intercept, would get added in kind of to every single one. So if I'm just trying to make the prediction for what their wage would be, I would have to include the intercept for every group. Now, the effect relative to the group I left out would simply be, right, I would kind of ignore that constant, right? So, another way of thinking about this, let me see, I'm going to make sure you can see all this still. So if I want to know, and I'm just going to write wage, we're going to ignore the natural log just for a second. If I wanted to know, well, how does wage change for a female, right? Well, I'm going to have a derivative of my linear regression, right, or my equation in respect to female. So I'll be left with beta 1 here plus beta 3 times married. So notice the effect of being female in my wages is dependent on whether or not I'm married. If I'm an unmarried female, this would be a 0. the effect of being female is simply beta 1. So this is unmarried. If I'm married and I'm a female, the effect of being female on my wages would be beta 1 plus beta 3 times 1, or just beta 3. So really what we're doing here, right, is we're picking up, if I have this linear regression equation, it gets kind of weird to think about. We would really want another continuous variable in there that we could kind of graph out. So I'm just going to use age. Well, actually, this is beta 4, right? For a second. So let's just say I was thinking about predicting wages using age. Well, beta 1 plus beta 3, this would kind of be beta 0 as well, would be like my intercept for a married female. So I'm picking up kind of differences in that intercept of where that line of best fit would start out. Now, we'll get a cleaner version of what that line of best fit looks like when we actually have an interaction with a continuous variable. Really, we've kind of already done this, right? So I created 4 groups. One of them got left out. We've actually already done this before. This was when we had a categorical variable. And what did we do? We could use like the IDOT command in Stata, or we included every single group, a dummy variable for every single possible group. We just left one of them out. That's really what we did here. It's just not quite as clear, right? Here was my first group, unmarried females. Here is my second group, married males. And here is my third group, married females. And we had left one of them out. So it's just a different way of doing what we've already done, right? So instead of starting with a categorical variable and then creating the dummy variables and including all but one, if you interact 2 dummy variables, that's really doing the same thing, right? We're just picking up on differences between these groups' starting points, okay? But we can think about then the marginal effect of these dummy variables might vary across whatever group we've interacted it with, okay? Any questions on anything I said here? Yeah. Mm-hmm. Yeah, so you can think about if we start to include more control variables, all these dummy variables do, we said with dummy, all that does is it changes my intercept. It's not going to change the slope of any of my lines of best fit, right? It's just going to kind of change where that prediction is going to start out for that group.
So like predict the intercept for like beta 0 plus beta 1 plus beta 3. That's the intercept with married females.
Correct.
But beta 0 by itself.
So that's going to be, so this was married females. What would beta 0 be? What's the only way I start out at beta 0? If everything here is 0, which would mean I would have an unmarried male, right? So you can kind of think about here, this would be the starting point for an unmarried male. And then we could plot in the other 2 different categories as well. Yep. Any other question on that before we keep moving? Yeah, go here.
When you beta 3 times the variable beta 2
Over here.
right.
Here. So if I'm making the prediction for where a married female's, oh, I forgot one. What did I forget? This was the marginal effect, sorry. If I'm plotting the intercepts, if I wanted my married female group, I would have beta 1, beta 0, beta 1, beta 3. I would also have beta 2. Yep. And then if I only had married males, then I would just have beta 0 plus beta 2 and so on and so forth. Yep. So we'll go through another example I think will also help. So I've got my marginal effect here of being female. What if I wanted the marginal effect of being married? So once again, if I've included dummy interactions, this marginal effect, right, is going to be different for 2 groups. So now if I'm looking at the marginal effect of married, there's going to be a different effect for males than there are for females. So if I take a derivative of this function in respect to being married, but for males, right? Well, if they're male, what's true about the female variable? It's 0. So even when I take a derivative of this, it would be what? Beta 2 plus beta 3 times female. But if this is 0, what's the marginal effect of being married for males? Just beta 2. Now, when I take a derivative, it looks the exact same when I do it for females. The only difference is now this variable is a 1. So kind of the marginal effect for females would be not just beta 2, but beta 2 plus beta 3. So if this was negative, that would kind of tell us the effect of being married on your wages is actually lower for females than it is for males. If it was positive, that's telling us that the effect on wages of being married would actually be greater for females than it would be for males. Excuse me. Okay, so there's a slight difference when we're thinking about kind of where that predicted Y value starts out and when we're talking about the marginal effect. Any questions here before we go back to the slides? So when you think about the marginal effect or the effect of something, we used to not have to take derivatives because when it was just a linear model, if we take it really would have just been just the coefficient. Now we've got a couple more things, right? That variable shows up more than once. Just like when we were thinking about that squared term, we had to take a derivative of the linear and the squared term, right? We've got it showing up in multiple places now. So let's think about kind of if we ran that regression, what is that going to look like? So one thing that we can do is we already talked about, if I want to multiply a variable by itself, we did this before with multiplying a variable, sorry. When we did it before, it was multiplying a variable by itself. We used that double hashtag. Now, we're not dealing with continuous variables, so we don't have to put C dot. There's 2 dummy variables, but instead of creating a new variable where I say, generate this new variable, which is female times married, I can just instead of put double hashtag. That will include female, it will include married, and it will include the interaction between the two. Now, it's weird, it starts throwing ones in front of here. That's just kind of the syntax, but if it's easier to look at, you could create your own variable, but this is a kind of a shorthand way of doing it. So if I'm looking at this, what is the total effect of being on my wages of being female? What is the change in my predicted wages? So what's the marginal effect of being female if I'm unmarried? Well, there would just be negative 0.25. So this would predict that holding everything else in this regression constant, their experience, if they belong to a union, their health, you've got some racial identifiers, some regional identifiers, a bunch of different stuff, holding everything else constant, but they're female, their predicted wage is actually going to be lower. And we can say that at highly statistically significant levels, right? 99.99% here if we really wanted to. Okay. Now, what is the effect or what is the predicted change in a female's wages if instead of being unmarried, they are married? Well, not only would they experience that kind of, not premium, but the dispremium, right? Actually, reduction in wages of 0.25, they would experience a reduction in their wages on average of 0.25, as well as, well, they're married, so this would also be part of the effect of being female now as well, right? This would be the total effect of being female for an individual who was married. Right? So basically, relative to a married male, the married female would expect an additional, what, $0.21 per hour, however we're measuring wages. This isn't log, so it gets a little bit different, but right, another reduction, right? So they're kind of being penalized not only for being female, but then also again for being a married female, right? Whereas, what's the effect of being married for males? Right? I know employers think they actually have your shit together or something like that if you're a married male, right? So we've got kind of all of this being highly statistically significant. We can start to see that maybe certain groups will be that the marginal effect of another variable might vary across those groups. This is a pretty good example of that. Right?
So the female by married variable, is that the marginal effect? Is that what it's described?
So that'll be a component of the marginal effect of being married and a component of the marginal effect of being female. So remember, when we were looking at the marginal effect of being female, so the change in wage from being female, it was beta 1 plus beta 3 for a married female. When we were looking at the marginal effect of being married, it was beta 2 plus beta 3. So that interaction term would be a component of the marginal effect for both groups. Well, it would show up in two marginal effects, right? It's not going to show up for the males, but it's going to show up for differently for females if we're looking at the effect of being married, and differently for individuals who are married if we're looking at the effect of being female. Yep. So just to interpret beta 3 on its own is a little tricky because it's really picking up the effects of two things. So if we think about trying to interpret just beta 3, well, we have two variables that are changing. So really beta 3 is telling us two additional effects, right? So when we go back here, so our beta 3 was negative 0.21. So here it's telling us the additional effect of being married, if I am female, is that the effect of being married on my wages is about what? 0.21 lower. But it also tells me that if I want to know, well, what's the effect of being female on my wages? If I'm married, it's also 0.21 lower. So I would never really ask you like just to interpret beta 3 because there's not really one clear interpretation. It's picking up both the effects of being married and female and allowing me to identify the differences in the marginal effect of multiple variables at the same time, right? So when I'm multiplying these two variables together, it's not, a 1 unit change. Well, if I've got two variables that are changing, how can I have a 1 unit change? Only one of them can change at a time. So I really don't have a nice clean interpretation of beta 3. So it has, in theory, it actually has kind of two interpretations. It's the additional effect of being married for females, and it's the additional effect of being female for someone who is married. It's not quite saying the same thing because my comparison groups here are different, right? My comparison group here would be to unmarried males. My comparison group here would be to married males. Or I might have said that back. The effect here would be the comparison to married males, and here it would be compared to unmarried males. Yeah. So I won't ask you to interpret the interaction terms coefficients, at least for these dummy variable models. Yep. Okay. Any other questions before we jump back to the slides here? Okay. All right. So kind of already went through these. We've already talked through all this. I can show you how to do this in Stata. Although before we jump to Stata, I want to show you something else first, just so I make sure we kind of get through it, have enough time to get through it today. Okay. And really, I think looking at this output, it's not going to be that hard to do this in Stata, right? It's really everything we've done. It's just using the interaction between two variables. So you can either create that variable or use this double hashtag that we've already kind of talked about to like create it for you. Now, what might be different? So let's say I'm going to jump the gun a little bit and we'll deviate from this, but maybe I use this example on the in-class quiz. I think it's kind of a, I don't know if fun one's the right word, but so let's think about mate height. I'm thinking about humans, but if it helps, you can think about this as elephants or whatever other animal you want to, right? We can try to predict that using an individual's own height, whether or not they're male. Actually, I think it'll make it easier if I do it this way first. Whether or not they're female. And then I think, okay, if I was trying to predict what I think these coefficients would be, so if you look at Tinder data or something, or Bumble or whatever hell app you use, if someone is taller, what do you think tends to be true about their predicted mate's height? I think it tends to be higher or lower. It's kind of tricky. You would think it might be, yeah, so you would think it might be higher. Although we'll see, this isn't always statistically significant. It tends to be that maybe they just don't care as much. If you're taller, you don't really care, right? Everyone's shorter than you. That's part of it. But yeah, you would expect that maybe this would be positive, right? Now, if you're female, just by the law of averages in biology, what's true about your predicted mate's height? We're looking at heterosexual couples. This would have to, by law of average, be males are on average taller. I'm not rewriting, biology books here, right? So we would expect that these things are positive. Now, what if I included kind of an additional interaction term? So when a female is taller, right, do you think the additional effect, so let's say when we're looking at a female, if they're 1 inch taller, do you think the additional increase or sorry, the additional change in their mate's height, do you think they're going to choose on average taller or shorter, I don't know, mate, partner, whatever you want to call it, than a male would? So if I'm looking at like a 6 foot tall female, do you think that them being tall is going to have a larger or smaller impact on who they choose to be with compared to a 6 foot tall male? On average, I'm guessing most females want someone who's taller than them. That I'm speaking in generalities. This is obviously not true for everyone. Once again, if you don't like this, I didn't make up the Tinder and Bumble data that's out there. We've got some data. I'll actually prove this to you. Okay. So it's likely that there's going to be an additional effect of being 1 inch taller if I'm female compared to if I was 1 inch taller and I was just male. Okay? So notice here, we've got a dummy variable, but what is height? Height is a continuous variable. So if I wanted to know, well, what's the change in my chosen mate's height if my own height goes up by, and I'll talk in inches here, goes up by 1 inch, right? Well, what is that marginal effect? It would be beta 1, if I take a derivative of this function in respect to height, plus beta 3 times female. So the marginal effect for a male would simply be beta 1, right? Because this would be 0. The marginal effect for a female would be beta 1 plus beta 3. Once again, my imagination would say I would expect beta 3 is probably positive here, but if we're looking at a different example, it could be anything, right? The marginal effect could be higher, could be lower for this other group. So this might be something we'll look at with the in-class quiz stuff, but we'll kind of jump to a different example here in a second as well. Because I'm not looking at the predicted height. What am I writing out here? I'm writing out the marginal effect of height, right? If I'm making predictions for what that person, this chosen height would be, yeah, I would have to use this entire equation. Just like if I was using a quadratic model, I want to know what's the nonlinear relationship. Well, when I was looking at the marginal effect, I was only taking a derivative in respect to whatever variable I squared. Right? All my other controls, when I take a derivative in respect to this, they're all go away, right? So for example, if I had like age in here, when I take a derivative in respect to height, what would that be? Is height part of this? So if I take a derivative in respect to height for this component, this would just be 0. Doesn't exist, right? There's nothing there. I can't take a derivative. Height isn't part of that. So we're talking about the marginal effect, not the predicted value of y. If I wanted to come up with predicted values for y, I would not only use height and female, I would use every other variable in the regression. Does that help clarify it a little bit?
Yeah, just one more clarifying question. So it said beta 1 plus beta 3 times the female. Since beta 3 is height times female, would I read that as like height times female times female?
This?
Yeah.
So if I take a derivative, not y, z, right? If I take a derivative of this function, I don't know why I just said derivative that way, in respect to x, what does that become? Yeah, the x goes away, right? I've taken the derivative. That's why height goes away. We're looking at the change in mate height from my own height. We're taking a derivative in respect to that. You can just think of it as it's a variable, right? If it helps to think about it as x, you could put x in there and then take the derivative. Does that make more sense?
Yeah.
That's a good question. Any other questions that we have here before we keep moving? So we see this happen a lot with, so if I'm then wanting to come up with a line of best fit for that relationship between height and mate height, it's a little bit tricky here. So if I'm coming up with my predicted mate height, so this goes back to now, we're not thinking about marginal effects. Where would, and I'm not including age for the sake of simplicity, at a height of 0, right? What would my predicted mate height be? Well, it's going to vary on if I'm male or female. If I'm male, what would my predicted, so I was writing things in here, so let's just write this out again. So beta 0 plus beta 1 times height plus beta 2 times female plus beta 3 times height times female. So where would the predicted mate height start out at for a male? So if they're male, height is 0. This would be 0. What's the only thing left in my equation? Beta 0. Now, if they're a male, what's the what would that change in mate height be if their height starts to go up by 1 unit? So what would the line of best fit look like for males? Well, if male height goes up by 1, well, remember, they're male, this would be 0. The only change in mate height is going to be beta 1. Now I'm drawing it upward here because I'm assuming for both that as you're taller, that you're choosing someone else who is taller. It could be negative, but for the sake, I have to draw one thing, right? Now, what if I'm thinking about females? Where would their predicted mate's height start out? If they were 0 inches tall, right? Where would the predicted mate height start out at for females? It would be beta 0 plus beta 2. Once again, I'm assuming beta 2 here is positive. It could actually be that it's negative and it starts out lower. Now, when I think about this change here, as the female gets higher, so I'm using different colors, so this would kind of be my line of best fit for my 0 group or males. What would the line of best fit be for my 1 group or the females? Well, as they get 1 inch taller, their mate's height goes up by beta 1, but it would also go up now by, if this is a 1, when height goes up by 1, it also goes up by beta 3. So the slope, assuming that beta 3 is positive, would look something like this. So we already talked about this a little bit, and that dummy variables allow me to identify differences in like the starting point of my line of best fit. But before, when I was drawing them out, I drew those groups lines of best fits as parallel. When I include the interaction term, what can I now allow? Well, I allow for a different starting point for that group, but I also allow for the marginal effect of whatever x variable I'm graphing here to be different between the slopes can now be different. Right? Now they're still linear, right? But they don't have to be the same linear value. I won't do this to you guys, but you can imagine, what if I thought for some reason like male height was linear and female height was quadratic? I can include interactions with the squared term and do a kind of combine. We're not going to go that far, but you could do that, right? Here, we're just going to allow there to be different linear relationships between the two groups or different slopes. Any questions on this before we keep moving here? All right, so got another example. It's going to be very similar, all right? And we'll jump to, like I said, I've got an in-class quiz that we should have time for at the end. But I'm going to go back to that wage data, right? I'm going to think about, okay, maybe females, we already saw there was like a negative coefficient there. This data set also had this weird measure of beauty. It was like this goofy, like they showed them pictures, like random groups, and then had them rate them from 0 to 5. I know, very weird and creepy. But they were trying to come up with some way of like, is there a premium paid to people who look better in the workplace, right? So not only did they have this nice continuous variable, it was like I said, I think it was from 0 to 5. But they said, well, you know what? Maybe women and men are rewarded differently for their looks in the workplace, right? And so this might be an additional thing that is driving differences in wages, right? So they included an interaction term between this continuous variable and this dummy variable, which is just an identifier for if they were female or not. Now, we'll look at the actual results and then we'll graph it out. I won't ask you to kind of predict this. But beta 2 is going to be kind of the difference in our what? We had 2 lines of best fit for this relationship between beauty or looks and wages. Beta 2 allows for a difference in the what? So I'm predicting this line of best fit for the relationship between beauty and wages for both males and females. So beta 2 is going to tell me that where that line of best fit starts out, right? The difference in where it starts out, right? It's going to shift my intercept. The interaction term is going to allow me to identify differences in the slope for that line of best fit between the 2 groups. So I've got this regression. We'll then kind of plot this out. I'll give you a nice visual. But here, I've got looks. I've got, whether or not they were female. I don't have the interaction term yet. So I think that's on my next slide. But we can kind of start out here. Go ahead and get this to go away. There we go. So if I don't include the interaction term, I'm going to look at this. I'm like, oh, look, looks like being female has a huge negative effect on your wages. Looks like as your looks rating goes up, you tend to be rewarded. You tend to get higher wages. And both of those are statistically significant. But maybe it's that those looks are really not kind of coming from both male and females. Maybe it's only that one group is being kind of rewarded for their looks versus the other. Or, so we can kind of identify, explore this. So we're going to include an interaction term. So once again, a nice shorthand. I can start using this double hashtag as opposed to creating new variables. If I want to create the new variables, I can, right? But I don't have to. Right? I can use this double hashtag. The only problem is now we don't have a dummy times a dummy. So we go back to thinking about the nonlinear relationships. If we use this double hashtag instead, we said we're going to have to use a C dot in front of our continuous variable, which here was looks. So here we've got now, if I can control for looks, what does it look like the effect of being female, that coefficient, that starting point? Before it was like what? Negative 0.38. Now that starting point for females, even lower, right? However, if I'm thinking about the relationship between looks and wages, it's about 0.04 for males, but what is it for females? 0.04 plus another 0.046. So what's going to be true about the slope of that line of best fit for that relationship between looks and wages for females? It's going to be steeper. Right? So we can kind of graph this out. What would this look like? It's going to look a little bit different than the last one we did. So instead of like mate height now, we're looking at kind of wages. And we want to know this beauty or looks variable, kind of what that relationship looks like. So for, here we'll do wage equals beta 0 plus beta 1 times looks plus beta 2 times female plus beta 3 times looks times female. Okay. So this was what, about 0.04. I'm going to do some egregious rounding here, but for the sake of this, I think it'll be all right. And this was negative 0.53. Okay. So I'm going to draw 2 lines of best fit for this relationship between wages and looks or beauty, right? One for males. So if I was doing this for males, where would the predicted kind of male wage start out at? Well, this would be a 0. This would be a 0. Where does it start out? It would be at a looks of 0. So the predicted kind of starting point for males here would be beta 0. Now, as looks goes up by 1 unit, what's going to be the predicted change in wages for males? Well, this is 0. This is 0. So if looks goes up by 1 unit, the only thing changing it would be, beta 1. So this is kind of my predicted wages in terms of kind of looks for males. Now, what if I want to do the same thing for females? Where would their wages start out at? So instead of, oh, and I didn't put what beta 0 was. I don't know if I had it on the slides. It doesn't matter. Let's say it starts somewhere, right? Where would the predicted starting wage be at for females? beta 0 plus beta 2. Well, if beta 2 is negative, it's going to be somewhere down here, right? Somewhere below where males started out. However, as looks goes up by 1 unit, the wages or the predicted wages won't simply go up by 0.04 like they did for males. They would actually go up by 0.04, but now this is a 1. So when looks goes up by 1, it also increases by beta 3. Beta 3 is 0.046. So we have my predicted wages for females. Now that slope would be beta 1 plus beta 3, or 0.04 plus 0.046. So almost, more than twice as large for females than it is for males, right? So I guess, this is being a bit glib and not probably politically correct, but I don't care that if women are paid less if I'm a good-looking female, because I actually get paid better than my good-looking male counterparts, right? At this point, right? Now, obviously, I'm joking. None of this is good, right? None of this should really impact your wages, right? This is actually that's the bad part of the story, is both of these things shouldn't impact our wages, right? But we can start to see, okay, not only are women kind of being treated differently from the fact that they're simply being women, right? Controlling for what their looks are, but they're also kind of, these two groups are being treated differently depending on what their looks are, right? We probably don't want that in society either, right? In terms of just being paid. I guess if this is, I don't know, modeling gig data or something, maybe we, don't have a different opinion, but if this is just from regular workplaces, this is a bad story, right? Any questions over anything here? Yeah.
Can you just briefly explain why beta 1 plus beta 3?
Yeah, so it's different groups, right? So once again, if I wanted to know the marginal effect, so when I'm graphing this out, I'm really graphing out the relationship between my y and this specific x variable, right? So I am really graphing out that slope is telling me the change in y from a change in x, or for us, a change in wages from a change in looks. So if I take a derivative of this equation in respect to looks, what am I left with? Beta 1 plus beta 3 times female. So what is the marginal effect for males? Well, if they're male, this is 0. The marginal effect is simply beta 1. If they're female, what's the marginal effect? Well, this would be a 1. So now the marginal effect is beta 1 plus beta 3. So the reason why we get to add it in is because we're allowing, that interaction term is allowing for that marginal effect, the slope of that line of best fit, to vary between this group that we interacted it with. Is that?
Yeah, that makes sense. I guess I'm just not understanding it. Like from the derivative.
So once again, these are just variables, right? So this would be x, this would be z. Anytime I'm interacting, my marginal effect is going to be, so if this was x, take a derivative in respect to x, I'm left with beta 1 plus beta 3 times z. Well, there my marginal effect depends on what z is. I have to know what z is. Now, in my example, I've actually kept it easy up to this point. We're going to make it harder next week. Right now, z can only be two values, right? 0 or 1, right? Two different groups. What could be true from a mathematical standpoint, z could also be continuous, in which case my marginal effect depends on not just being 0, 1, but what level would z be. So, I mean, taking a derivative of this function in respect to x, I'm left with beta 1, beta 3 times z. Yep. Good questions. Any other questions on this? Like I said, we're going to get the continuous interactions are rough next week. They get a little bit harder. Okay. So make sure we got a good base understanding of this before we kind of progress to that next week. Any other questions on this? Okay. Let's think. Oops, didn't want to do that. There we go. All right. Now, when we include these interaction terms, this is where we want to be careful. Right? Once again, similar with nonlinear, I've really got two things I can compare here, kind of. I might think, but really only one of them is what I should be using. So if I go back to my regression without the interaction term, what's my R squared? 0.407. When I include the interaction term, what is it like I'm including? When I'm writing this out, I'm including an entirely new coefficient, which means I have an entirely new variable that I've added. So when I add a variable, what's going to happen to my R squared? Has to go up. Anytime you add a variable in, the R squared has to go up. So just because my R squared now is a little bit higher, so instead of 0.401, it's 0.407, well, I knew it was going to go up. Now, what adjusts for that? My adjusted R squared. So that's actually going to be, I don't have a bullet point here. That's what I want to compare, right? Because that adjusts for the fact that I added an additional variable. So my adjusted R squared going from 0.4014 to 0.4016. Okay, it looks like this interaction term increased the amount of variation I could explain in wages by a little bit, right? Out to the fourth decimal, but a little bit. Okay? So instead of comparing our R squared, when we're adding in this interaction term, we have to compare our adjusted R squared. It's the same thing with nonlinear relationships. If I want to compare my squared model to my linear model, I can't use my R squared. I know it's going to be higher. I included another variable. What accounts for that? My adjusted R squared. Excuse me. Okay. Any questions on that before we keep going? Yeah.
I think it's back to more with the graphing, but
Mhm.
when you were doing the marginal effect,
Mhm.
like when you're graphing, you assumed that males and the books had a continuous, like the marginal effect didn't really increase versus the females had an increase in marginal effect. What would happen if both variables had an increase in marginal effect, like being males and books and females? How would you be able to tell that?
So when we're looking at the marginal effect, I'm not assuming that anything about that relationship. I'm just allowing it to be different. So here, the marginal effect is positive for males. I can pick that up in simply that looks coefficient. I can allow for that looks effect to vary for females. So if I had more than two groups, I think is maybe kind of what you're getting at. I won't push that. We only have two groups. So we have to have a comparison group. So we have to have that zero group. That's where the kind of marginal effect starts out. Now, because we included the interaction term, we can identify if that marginal effect varies for the one group relative to the zero group, or for females relative to males. If I have more than two groups, it's a little bit trickier, right? But yeah, I haven't assumed, and in fact, this could have been negative. I could actually have these lines going in opposite directions. So where did I write it out? So imagine like this was 0.04, or I don't know, let's say this was negative 0.04. I would actually have the line of best fit for males being downward sloping, but then for females, it would be slightly positive. So the marginal effect for these two groups, in fact, could be different signs. Right? Not only could they be different values, like just magnitude-wise, they could be completely different signs. Does that help or is okay? Any other questions here before we keep moving? Okay. All right. So we can look at the adjusted R squared. What else can we look at? Basically, the statistical significance of that interaction term. So even though I found a difference here, can I say that females' wages are impacted differently by their looks than males are? Well, the additional effect of looks was this interaction terms coefficient. Can I say that that's statistically significant? Not any of my conventional levels, right? So although I can identify if there is a difference in the effect, well, just because I find a value, that doesn't mean that it's statistically different. So I can plot out the values, right? But in terms of statistical significance, I can't actually say that there is any difference in those line of best fits between males and females. because it's p-value, the p-value on my interaction term doesn't meet my thresholds, right? It's here 0.24, a little bit higher than 0.1, 0.05, and 0.01. So this would indicate that I don't really need to be including the interaction term. There isn't a statistically significant difference in the effect of looks on wages for males versus females.
More out of curiosity.
Hmm?
Would there ever be a case?
Well, if I fail to reject, what is the coefficient of the interaction term? I always start out assuming it's, yeah. So yeah, you could find it's 0, but in practice, you'll never find 0. You'll just find a value and then fail to reject, right? Or something very close. You could find something very close to 0 and fail to reject as well. But yeah, by failing to reject, we really are saying that interaction terms coefficient is 0. Yep. Think of another one. Well, I'll do one here because I know because I grade everything in this class. Your hours of studies effect on your exam score interacted with whether you're female or not has absolutely no effect, right? I could run that regression. I can guarantee you the interaction term is going to be 0, right? Because when I'm grading these, I don't even look at the name. So I don't even know who's I'm grading at that point in time, right? So, you could run regressions and end up with interaction terms that have coefficients very close to 0, which just tells you that there's no interaction between these two variables. Yeah. All right. Let me think if there's anything else I want to say. We already talked about, we know the R squared is going to be greater, so we want to use the adjusted R squared. I also want to say here, I think I have this kind of written out just in more general terms. So this goes back to like if I'm using a dummy variable and any continuous variable and then including an interaction between the two, right? So this is more of like a general summary. Beta 0 will always tell you the intercept. So when we're graphing these, that was all the intercept for my 0 group. Beta 0 plus beta 1 would always be the intercept for my 1 group. Beta 2 is going to be the slope or the marginal effect of that continuous variable for the 0 group. And then beta 2 plus beta 3 is going to be the slope or marginal effect for my 1 group of whatever X variable we're looking at. So this is just kind of written out in general terms without specific variables. This will always be the case. So this might be a good one as you're going through the problem set, even the quiz. Well, sorry, never mind. That's old stuff. The next quiz and problem set we have might have some interaction stuff. This might be a good slide to kind of have in mind. Okay. Questions on that? It's just things we've already kind of said here. We've already talked through this. For the sake of time, I want to make sure. So I had some stuff that I thought was interesting. We'll come back to it if we have time. If not, we'll start on Tuesday's class. So I'm going to publish this. And I'm going to give you guys a little bit of time to work on this. The other people around you. Oh, I want to preview it. How can I do that? Hold on. So you should now see this pop up. Oh, I know how to do it. So I use the new quiz option because there were some interesting things here. Preview. All right. So you're going to have 3 questions here, right? Graded for correctness. Given how many people are here, maybe hold off on submitting. Maybe we'll kind of go through these together. There's going to also be a number of the day, which I haven't given you yet, that gives you the kind of base 2.5 points. If you're paying attention at all today, by the end of this class, you should get all the points, right? It's just my way of penalizing people who don't show up. No, I shouldn't say it. It's my way of incentivizing people to show up, right? So talk to the people around you. I kind of went back to this mate height example. So we've got a continuous variable. We've got a dummy variable. I've got some regression output. Try to answer the following 3 questions. All right, this will be good practice for you, not only to identify maybe things that were kind of getting lost in translation that you weren't quite understanding, but applying what we talked about from these other examples with some actual numbers for that mate height example. So I'll give you guys about the next 10 minutes or so to work on this, and then we'll kind of come together. I might kind of help you out with some of it, and then kind of finish out the discussion today. Okay. Yeah, I'll encourage, look to the left, right, talk to people next to you, try to figure this out. Yeah. Did I accidentally hit it? That should be up there. Is it not showing up to you guys? It is, okay, okay. So go back to the homepage. If you go all the way down and click on in-class quiz number 8. Okay. Don't have to be quiet. So again, I'm trying to give you this time, so I think it's valuable to kind of work and have me as a resource. So try to see if you can reason through this with people around you, and then we'll talk about it here in about 10 minutes. We may not have talked about 2 yet. We've talked about enough where you can kind of reason through it. So I'll kind of give you a better explanation, but try to kind of work on it and think about what that would mean.
10 seconds. I've done all the questions. Just need today's numbers.
16.
16.
Okay. All right, we'll start talking about it a little early. So I've got this written out. I think the first question is what? Based on the output above, you're plotting predicted mate height for different levels of own height for males, and also graphing different for females, which of the following is not true. So I've got kind of the results written down here, at least out to the second decimal. So if I'm thinking about, I've got two lines of best fit, and I'm trying to think about the relationship that exists between height and kind of mate height here. So for males, where's the mate height going to start out, the predicted mate height? So if they're males, what would get added into my prediction? Well, where does it start out? That would be at a height of 0. So if height is 0, what's the only thing left in this equation? Beta 0, beta 2 times male. So for males, where's my coefficient going to be? Or coefficient. Where's my intercept going to be? It's going to be beta 0. This would be a 1 plus beta 2. So if I'm looking at this, that'd be what? 27.7. So I'm 37, approximately 38.7, right? I think this is inches, might be in centimeters. I forget what the unit was, right? So all I did here was I took beta 0 and I added the coefficient from my dummy variable, right? Which was male here. I changed it from the example I think I wrote earlier was female. Now it's male. It's very similar, but a little bit different. Now, where would female predicted mate height start out? Well, if their height is 0, they're female, this would be so their predicted mate height would start out at beta 0 or 27.7. So the intercept for females is going to start out lower. I forget all the options, but you know, if there's one that says it's going to start out lower or that males will start out higher, those are going to be true. Now, for males, we'll start with females. If females get 1 inch taller, what's the change in their predicted mate's height? Well, if they're female, this is 0. Well, it doesn't matter because it doesn't have nothing to do with height. This would be a 0. So here's where, when I'm thinking about my marginal effect of height, or really the slope of these lines of best fit, what would it be? If I take a derivative of this function in respect to height, I've got beta 1 plus beta 3 times my dummy variable. So for females, what would that marginal effect or what would the slope be? Well, this would be a 0. So the slope for them would just be beta 1 or 0.67. So for every inch taller that a female is, their mate's height goes up by about 2/3 of an inch. So it's not 1 to 1, but about 2/3, right? Now, what about for males? What would the marginal effect of the height going up by 1 inch be for males? It would go up by beta 1. This would be a 1 plus beta 3. So here I've got a negative value. So what my slope would be, just under what 0.39. Am I looking at that correct? Yeah, 0.39. I'm doing math in my head. So notice that slope beta 1 plus beta 3 is going to be a little bit smaller, or that line of best fit for males is going to be flatter. Okay, so I think that helps us answer question 1. Right. So we're thinking about here, male slope is flatter. Wait, that one now I don't have it. Oh, which one's not true? So yeah, that one's true. I was going to say, oh gosh, the intercept for mate height is greater for females. Is greater for males. We said that one was true. For females, the intercept is lower. That one doesn't even make any sense. So that one can't be the right answer, right? So that here it has to be the exact same thing. Here we're thinking about that female slope was going to be a little bit flatter. I should have got rid of this answer. I think I was just trying to plug in ones and kind of come up with something for class real quick, right? So hopefully everyone that's here today should kind of answer with I guess, C. I'm not sure if it's showing up to you different, but basically that female slope is going to be flatter. That's the one that's not true. Yeah.
Can you go back to, here?
Maybe.
The male one is beta 1 plus beta 3.
Mm-hmm.
Okay.
But because beta 3 is negative, right, that slope ends up being a little bit flat.
Oh.
Yep. Okay. Now, we didn't quite get to this one today, but we want to start thinking about sometimes these marginal effects. The way that I've been drawing them here, and in a lot of these examples, they'll always be positive or always be negative, but it can be that they sometimes will be positive or negative for different values of that continuous variable. So if I'm thinking about what's the marginal effect of, so what's the change in mate height from a change in whether or not the individual is male? So what would that be? So now I'm taking a derivative of this function in respect to male. So what am I left with? Beta 2 plus beta 3 times height. So here the effect of being male on mate height will depend on the individual's own height, right? So this is the idea, if I'm a, 7-foot tall male, being 7'1" probably doesn't change my, it might change my predicted mate height very differently than if I'm going from, 5'6" to 5'7" or something like that. Excuse me. So here we had beta 2 was 10.99. Beta 3 was negative 0.28. So notice, when height is 0, what's the marginal effect going to start out as? Positive, yeah. Now, the effect of being male on my mate's height, as I get taller, what's happening to that marginal effect? It's getting closer to, yeah, right? If its height goes up, I'm subtracting a larger value. There might be a turning point or a threshold where this marginal effect of being male, there's a height value where it will then become negative. So how would I find that turning point? Simply, yeah, set that marginal effect equal to 0. Now it's just a little bit of algebra here. I've got that turning point for height would be 10.99 over 0.28. So I don't know. I forget what value that ends up being. I'll give it to you here, but it's 39.83, right? Or approximately, right? So we can find where these marginal effects might go from being positive to being negative, right? When we include these interaction terms, okay? Now, in the examples I was drawing, things were kind of upward sloping and they were starting as positive, so that didn't kind of play a role. But here we're not thinking about the effect of the marginal effect of height. We're thinking about the marginal effect of being male, okay? Any questions on this before we keep moving? So what is this? So let's try to conceptualize this a little bit. What is this really telling me? So this was the change in my mate's height on whether or not it was male. So because it started out positive and became negative at higher values, that's telling me that when individuals are relatively short, what's the effect of being male on my mate's height? Same individuals, same height, but one of them's male. If the effect is positive, that means they're choosing a mate that's a little bit taller on average, right? And that as they get taller, right, two individuals who are both, 7 feet tall, but one of them's male, the predicted mate height for a female is going to be much higher, right? The predicted male height is going to be mate height for a male is going to be much, much lower. So it's starting to kind of pick up this idea that the effect of the dummy variable can also vary with values of that continuous variable, right? In fact, here, being male compared to being female, that might have a very different effect on mate height, depending on if I'm 5'2" versus 7'2", right? That's basically what this is saying, okay? Or allowing for us to identify. Yeah. So that's the nonlinear term. That's when we're going back to nonlinear relationships. That's what the marginal effect is. This is the marginal effect when we're looking at interaction terms. Yep. So we kind of switched subjects here today. Any other questions on that one before we keep moving here? Now, I think the third one should have been probably a little bit easier. Because I asked you for the predicted mate height for a male who's 69 inches tall. All you're doing there, if you're coming up with predicted values and you have your coefficients, male would be 1, height would be, what did I say, 69 inches tall. You just got a long linear equation, right? So using this interaction term to come up with predictions, it really should be the same as what we were doing before. You just have to kind of be careful with that interaction term. I need to be multiplying these two values, right? It's 69 times 1 times beta 3. But I don't think that's anything too wildly different than what we were doing when we were making predictions from just linear models without interaction terms. So I think if you do all that, you should get about 65.7, right? Does that, anyone come up with that? Yeah, I'm getting head nods. Yeah. So 65.7 for question 3 would be that predicted value. If you just plug in that 69, and then also it has to be a 1 because we're trying to make the prediction for a male. If it was the prediction for a female, what would be the only thing that I have to add? This would become 0. The only thing I have would be beta 0 plus beta 1 times height. Okay. All right. And then today's magic number, so that everyone gets this correct, is 16. I don't know why I chose 16. Maybe it's, I don't know, Sweet 16 starts today, right? Maybe that's why I did it, right? I had a reason when I wrote it, but I now can't remember. I think that's probably why. So 65.7, 16, 39.83. I've got a margin of error set on this, so if you were off by a decimal or so, it should still count it. And then the female slope was flatter. That was one that wasn't true. Okay. Before I let you guys get out of here, so you can get that submitted, hopefully get the full kind of credit for the quiz here today. We will kind of continue next week to look at interaction terms. I'll probably pick up where we left off, do another example. We'll then kind of move to continuous times continuous variables. It gets a little bit trickier, but we'll pretty much kind of just focus on this next week. We'll do a lot more in Stata next week. Today I was kind of trying to set us up just with the concepts of what we're doing with interaction terms. Other than that, you've got that problem set to start working on. You want to start studying for that quiz and take it before the end of next Friday. So not tomorrow, next Friday, okay? Any other questions for me before we get out of here? All right, hopefully we avoid the rain getting back wherever you got to get to. Have a fun, safe weekend. Oh, before you get out of here, I also, right, that's how girls see you when you're 5'11". A great meme to go with our topic today. So we'll pick up on this, kind of run through another example. I'll see you guys on Tuesday.